Hey friends, we have a new sponsor today, and I want to make sure that you support them because they make Hansel Minutes possible. RavenDB. It's a document database that's non-relational and fully transactional. It's available for Windows and Linux with official client APIs for .NET, the JVM, Go, Ruby, Node.js, and Python. RavenDB is designed for high performance, handling tens of thousands of requests even on a single node. Now, RavenDB is capable of on-the-fly optimization, dynamic indexes, and much more. It has a fully loaded GUI, which means it's simpler to operate, and you don't need, arcane incantations on the command line. It just works. It's fast and it's right. Download your free community edition at ravendb.net. That's RAVEN-DB.net. I hope you check it out. Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and today I'm talking with Charles Petzold. How are you, sir?
Good.
I taught a number of your books. I was taught by your books and taught one of your books in school. Particularly, my favorite book was Code that you wrote. I love that book.
Oh, thank you.
It's such a joy, the hidden language of computer hardware and software. And I understand that you're working on a new book, and who knows how long it'll take you to finish it.
The new book is, I've been working on it off and on for 15 years. And as I've been thinking about it and putting it off, it's gotten more and more complex. I've accumulated a lot more reference material for it. And so each chapter is like a couple book shelves full of reference material. It's just an enormous task that I've set up for myself.
When you're putting together a book that explores historical foundations of computing, the cultural context of computing, how do you make sure you don't accidentally write like 10,000 pages and take over a shelf?
It's hard. I have this particular book plotted out pretty well in my head, and I know what there's going to be 10 or 11 chapters, and I know what each chapter has to cover. But I'm going to really have to restrain myself to keep the individual chapters to about maybe 35 pages a piece. So the book comes in at about 350 pages. On the other hand, I don't think this particular book is going to appeal to a whole lot of people. So in one sense, I'm writing it for myself. And so I'm thinking I could just make the chapters as long as I want. And if the book comes in at 1,000 pages, I don't care. So I don't know. We'll see. It's a work in progress.
Do you write books for yourself, or do you write them for a mass audience? I mean, I read Code almost 20 years ago, and now 18 years ago, and I think of it as being a book it's kind of like the missing Tetris piece from my computer science education. Like it's that piece that they didn't teach me in school.
Yeah. I certainly wrote that for an audience. The audience that I had in mind were our parents. Many of my contemporaries who worked in the computer industry complained that their parents didn't know what they did for a living. And they would try to explain it, and of course, the parents would go glassy-eyed. As for younger people now, their parents actually do know a lot more about computers, but for my generation, they did not. So I thought of it as a book for our parents to show them what digital technologies were all about. And then I had these crazy ideas that maybe like actual politicians might read it to understand the computer revolution. I don't think that came about. But I did have an audience in mind. I always have an audience in mind.
How important is it for like new people? I talk about boot camps and self-taught learners and non-traditional learners, and even now computer scientists that have degreed computer scientists and software engineers come out without understanding the historical foundations of computers before, 1940, and without understanding the context within which these computers sit.
Yeah, it's hard to know how much this affects their perspective. What I became disturbed about was people who seem to be very fluent in high-level languages, but had no idea what was going on underneath. At least in C++ and C, we had pointers. And so to use a pointer, you had to really know the architecture of the underlying computer. But once computer languages pretty much abandoned pointers, as C# does to a large extent, even though you can use pointers in C#, it seemed as if the programmers didn't really know that stuff. So I hear from a lot of people who have been programming for years and sometimes decades who say, oh, I read code and now I finally understand how computers work. And that's really gratifying.
We always talk about how we stand on the shoulders of giants, and we think about each additional layer of abstraction as indistinguishable from magic. But at what point do you need to understand those layers of abstraction? Like you wrote another book called The Annotated Turing, where you guide people through Alan Turing's paper on computability. But does a JavaScript programmer need to know that? Or maybe they just want to know it if they want to understand the why, but it doesn't really make their job any easier.
Yeah, I got those questions a lot with Annotated Turing. How does this help the average programmer? And I really have to say not much. Except that there is this common presumption, and it's even in the movie about Turing, the title of which escapes me at the moment, The Imitation Game. Yep. All right, where someone describes Turing's paper as showing that any problem can be solved by a computer. And that's exactly what Turing's paper does not show. Turing's paper shows the opposite of that there are problems in mathematical logic that cannot be solved by a computer. In particular, the really big one is that you can't write a computer program that will debug other computer programs. You can get close, as the people in Microsoft Research have done, but you can't guarantee that a program is debugged entirely. That's a scary thought, that there is no way to guarantee that a program is entirely debugged. And so that should make us a little humble. Mm-hmm. And it should, if somebody gets a particular assignment from a boss that involves unsolvable problems, that they can say, computers can't do everything, including this problem.
Where did Turing exist in the spectrum of kind of mathematical computation, analog computers, digital computers? When he was thinking about this in 1936, what was a computer in his mind now that we've categorized them in ours?
That's hard to say. He was really kind of invented. It was really a intellectual tool, a tool of the mind, that a machine that would do something very methodically involving numbers, and would read symbols off a paper tape and write symbols back on the paper tape. And so he was really more of trying to formalize what an algorithm is. Where there's no intuition, it's just a matter of recipe steps. So Turing knew of no working computers. Around the same time, there were a couple people putting together what later became digital computers, but Turing did not know about them. He knew about Charles Babbage. So the idea, a lot of people knew about Charles Babbage. And so the idea of that a machine could be doing calculations wasn't entirely fanciful. From what I could understand, I don't think Turing knew anything about analog computing, which had been around, depending upon how you define it. Analog computing could go back to the slide rule, maybe. That's the 17th century. But the analog computers that interest me, one is from the 1870s. This is the subject of the book I'm working on. This is a tide predicting machine invented by Scottish physicist William Thomson, also known as Lord Kelvin. The other big one is Vannevar Bush's differential analyzer, which he built in the 1920s at MIT, and that solves differential equations. Both these machines, I think, are very clever, and that's why they interest me. And analog computing is really a forgotten chapter in the history of computing. When we say computer, we mean digital computer, and the history, likewise, is all digital. Even though there are people still alive who cut their teeth on working on analog computers. So it's not that distant in the past.
So to put this into kind of a little bit of historical context for some of the names that we dropped for people who are listening who may not follow this. So Turing conceived of an imaginary computer in 1936, while Babbage kind of invented the concept of a computer and was active in the 1850s.
Yeah.
So
even a little before that.
Yeah, 80 years, 90 years previous. Lord Kelvin built his tide predicting machine in 1872. So you said in 2018 that analog computers are a largely forgotten part of computing. Here we have Turing in 1936 not thinking about an analog computer that was created almost a century previous. It was a chapter that wasn't even in his mind while he was thinking about computing.
Yeah, primarily because he was attacking problems in mathematical logic, whereas the analog computers, particularly like the differential analyzers, solve differential equations.
Mm-hmm.
If Turing was interested in solving differential equations, he would have probably learned about the differential analyzer, but that wasn't what he was doing. So it's really it actually shows some of the divide, the big gulf between analog computing and digital computing, that they're used for two different jobs.
So analog computers are computers that use physical phenomena, things that are mechanical or maybe hydraulic or electrical to solve a problem. There's this wonderful picture that I'll try to put up on the show notes of this piece of hardware of wood and brass that is Lord Kelvin's machine.
Mm-hmm.
Maybe you could talk about what that does. It doesn't look like a computer, but it computes.
Yes. In the 1860s, Lord Kelvin, who was then known as William Thomson, got interested in the tides, and he developed a new process for analyzing the tides and predicting the tides. And what you do is you stick a tide gauge at some seaport, and this measures how the waters rise and fall over the course of the day. And you take a reading every hour. These tide gauges actually inscribe the height of the tides on a roll of paper. But you take readings every hour for a year or so, maybe a couple years. And then you apply Fourier analysis to it. And you break down the erratic up and down of the tides into sine curves. And these sine curves will have recognizable periods. They'll have periods of 12 hours, which is the effect of the sun on the tides. They'll have periods of 12 hours, 25 minutes, which reflects the effect of the moon on the tides. And they'll have other periods as well for resonance factors and all. So you apply Fourier analysis to it. You break down the pattern of the tides into separate sine curves, say about 10 of them. And then the tide predicting machine has separate wheels for each of these sine curves, each of these components. The wheel employs a mechanism called a Scotch yoke, which translates the revolution of the wheel to an up and down movement. That is the sine and the cosine of the wheel angle. And by these wheels, you can adjust a frequency, and with gears, you can adjust the frequency of each of these wheels, and you can adjust the amplitude and where it starts. And then, so you have 10 of these wheels bopping up and down in sinusoidal patterns, and you run a cable around them to sum it all up. And that's what you plot out on the paper. And the tide predicting machine, if you see the picture of it, when you turn the crank, all these wheels bob up and down, and there's a pen sketching out the rise and fall of the tides into the future, because the future is based on the summation of these sine curves that you derive from your historical data. The tide predicting machine, invented in the 1870s, is doing a summation of 10 sine curves. And that, to me, is fairly sophisticated in terms of analog hardware that doesn't seem to be calculating in any way.
Is this, as you turn this crank, are you effectively, and forgive me if this is an inappropriate diminutization of this amazing invention, is this basically a function wrapped in a for loop, physically?
Physically, yes. Not really a for. You see, a for loop is digital. Okay, because you're doing discrete numbers. Okay. I know
Right.
this is how
That's a very important and significant difference.
this is how our minds have been so imbued with digital concepts.
Forgive me.
As you turn the crank, it is more like if you think of the sine curves as mathematical functions, it's increasing a value of t time to apply to the sine curves.
And it's doing it in a continuous fashion.
It's doing it continuously, and that's one of the things that is so interesting about analog computers to me, because think about what it takes to calculate a sine curve in a program. We set up a for loop, right, with our angles, let's say 0 to 360 degrees, and we pass those angles, we convert them to radians and pass them to the .NET math.sine function. Okay. Now, what's a math.sine function doing? Well, internally, it's using the math coprocessor that's in your machine. And the math coprocessor, to calculate each value, is doing a summation of a bunch of terms involving factorials and exponents and all this. It's really a lot of number crunching that goes on to get a single sine value. And to plot out a sine curve, you need a bunch of these and tape them all together. Whereas in an analog computer, you're getting a sine curve, continuous sine curve with a fairly simple mechanism. Now, sine curves are found throughout nature. They are one of the fundamental rhythms of the natural world. And the reason why is that if you know differential equations, anytime you have a differential equation where a force is the inverse of displacement, a sine curve results, like a spring. If you stretch out a spring, the more you stretch it out, the more force you need to stretch it out. As you compress it, the further you compress it, the more force you need to compress it. The force that you need to compress it, and the force that it's exerting out is inverse to the displacement. So if you stretch out that spring and let it go, it'll go bouncing back and forth like a sine curve. Anything that it's elastic has this typical sine curve pattern. So that's why. So when you start looking at analog computers, getting sine curves is fairly easy. Whereas in digital computers, the only reason we think it's easy is because we have this math.sine function and it happens almost instantaneously. But internally, it's doing a lot of number crunching, which leads me to think of analog computing as a more natural representation of real-world phenomenon and digital computers as a kludge. It has to approximate this real-world process with a lot of artificial calculations.
Hey friends, just want to take a moment to thank our sponsors because they make Hansel Minutes possible. Are you struggling to reproduce problems in your code base? Well, successful software starts with Raygun. Raygun provides application performance monitoring unlike anything you've experienced before. It offers greater clarity around how your software is performing for your customers more than any other APM provider. I use it myself. You can easily detect and diagnose issues impacting end users. You can monitor every part of your stack in one place. It's time to get back to building great software instead of fighting it. Start your journey to better software quality. Try Raygun free at Raygun, that's RAYGUN.com today. It's interesting if you think the direction that we're heading, where we said we were sitting on top of the shoulders of giants, we're building all of these layers of abstraction on digital foundations in order to simulate reality, which is fundamentally an analog thing. And now, as we possibly hit the edge of what digital computers can do, we consider maybe quantum computers are the right way. Here we are again, a quantum computer is almost a kind of analog computer in that it is using the physical characteristics of reality itself to think about reality.
Yeah. On the other hand, quantum computers use a process that Richard Feynman famously pointed out, nobody really understands. So that's scary to me. We seem to be getting more and more divorced from our common experience. Um, there's a lot of analog devices and means of recording sound and pictures. I'll give you an example before I get off into abstractions. Let me give you an example. I don't know. I don't know your exact age or if you grew up with phonograph records.
I did.
But the grooves in a phonograph record, if you look at them closely, if you apply a microscope to them, you'll see that's little bumps in there. And those are exactly analogous to the waveforms of the air. Okay, so you can see, the little needle's moving up and down in the groove. And this is translated to electrical pulse. And this electrical pulse is then translated into a speaker vibrating back and forth. And we can hear the sound. We're hearing an exact analog of little bumps in the record groove. Whereas nowadays, what are we hearing? We are hearing a waveform that is reconstituted from a bunch of numbers. And I'm not saying this is inferior. And I'm certainly not saying that we should start using analog computers to replace digital computers, because digital computers, they have this big advantage. They have this major advantage that they're fast and they're extremely accurate and they're cheap and they're tiny. And so it doesn't make any sense to do anything else. I listen to CDs and I listen to Spotify. That's how I get my music. I'm not one of these people who still have a turntable and put my records on and put the needle down on them. I'm as immersed in this stuff as anybody, but there's still something missing. We're getting more divorced from the actual phenomenon.
And I wonder if at some point these abstractions are going to leak. The amount of work that's required for a digital computer to do something to represent reality is out of control. It's amazing. I just saw that they're now releasing an NVIDIA GPU that has the strength to do ray tracing. And I remember doing ray tracing. You would start the ray trace and you get a single frame, the following day. And now they're doing 120 frames a second, 4K full ray tracing. But again, trying to represent how light behaves and works using digital abstractions. So you've been working on this book for 15 years, and you maybe have a few years to go. Do you think this warrants a whole book?
Yeah, we'll see. Well, I started off 15 years ago, and I thought I knew how to write this book. And I thought it was going to be a mix of a little history and some physics and math and all. And as I wrote a couple chapters and started putting the math in there, and I was extremely unsatisfied with it. It just didn't flow right. And to me, math is laziness and when you're writing. It's like if you want to, you put an equation into your prose, and the equation is very clear itself because it's math. There's no ambiguity about it. But on the other hand, a lot of people can't read that. And so I got lazy doing that. And I eventually decided that the book would have no math in it, and that I would need to explain a lot of these things. And I would need to get to a point where the reader intuitively understood why sine curves are so prevalent in the natural world, and get to a point where they could see this machine and know what it did. So that's going to be harder. I also read one of the most influential books I read for myself, for my own writing, came out a few years ago. The author is Richard Holmes, and the book's called The Age of Wonder. And it's about science during the late 18th century, early 19th century, what's called the Romantic Age. And there's no math in it at all. There's no hard science in it. But this guy covers the science in terms of literature and poetry and art and politics and all that. It's all connected. And I thought, this is what I want to do. I want to have a good cultural context for this stuff. So that's what's forcing me to really do it. Really forcing me to not be lazy, to really do a good job on this. The other thing is that this machine and the reasons why it was built, which is another why Lord Kelvin built this machine, why he got interested in the tides, was related to his opposition to Darwin's theory of evolution. That, to me, that this was part of the Darwin Wars. This machine, one of these an early computer, makes the subject very sexy to me. Because you get into a lot of juicy stuff. So there's a lot of other pieces of science that fall into it. There's the astronomy, because tides are based on the movement of the moon and the sun. And there's analyses during the French Enlightenment of vibrating strings. And there's the Fourier part of it. And then there's the geology, because eventually Kelvin tried to figure out the age of the Earth. And he came up with something like 100 million years, and he didn't think that was long enough for evolution to occur. So there's a big geological component of this story. So it's a lot of different pieces of scientific history that come together in this one machine. And that is just, if it's going to take me the rest of my life to write this book, so be it.
Let me ask you this: as I have a 10 and 12-year-old entering middle school and soon high school, where would they learn this? Where would I fit a book like this into their curriculum if you've got geology and history and technology and history of computing and the political and socioeconomic context of the 1600s? And where would the Darwin Wars be taught?
Everybody has this sense that Darwin was controversial at the time that Origin of Species was published. I mean, good Lord, it's in some circles, it's still controversial, as we know. A lot of this stuff is really academic books about the conflicts during that period. I'm trying to make this book be as popular as possible. I'm not putting any math into it. That's something. So I don't know. Right now, I'm not sure what would be a good book for young kids to learn the history of science. Let me think about that, and I will let you know, because your kids seem so inquisitive, and it's just great. It's every time you post about your kids, it's like, it's often hilarious, but they must be amazing.
Well, I hope they will, if they continue to absorb good information like this. And I was fortunately able to read the first chapter of your work in progress. And I must admit, after going through 5, 6, 7, 8 pages, I'm thinking to myself, here comes the equation that's going to make me feel not clever. And there you go. There's a triangle with a circle and arc being drawn in a pencil. And I said, oh, isn't that accessible? And then I got a couple more pages in and there's a picture of the Earth. And I must say, I felt like I was reading something that was a smart person book, but I didn't feel like I was being expected to understand, Latin symbols for summation.
Good.
Which is a nice feeling. I appreciate that. So if you're writing this book, are we just going to follow you at charlespetzold.com and then watch and learn as this comes to life? We just wait until it comes out?
Yeah, I hope to post chapters. I'm not sure about posting every chapter in progress. That may be a little also anticlimactic when the actual book comes out, if it does come out. But yeah, I'm going to be posting more on Facebook as the book develops, on Facebook and my blog. So yeah, charlespetzold.com. It's not I really need to do a major upheaval on the website, but that'll be coming as well.
No worries. I really appreciate you coming on the show. And the working title is Computer of the Tides. And I just have to say, I love that title. I think that's just a wonderful title for this book.
Cool. Thank you.
Well, thanks so much for talking with me today about all these things. I'm going to include links and show notes so that you can go and explore analog computers and Babbage and Turing. And of course, go to Amazon and search for Charles Petzold to check out many years of great books, all recommended so much. This has been another episode of Hansel Minutes, and we'll see you again next week.